and then make it full screen. Where is Antonio? What? Okay. View. Don't need that. Cross this out and let's leave the chat over here. Okay. Let's continue with Fourier series. So goal today, talk a little bit more about Fourier series, get an introduction to a different type of Fourier series called the trigonometric Fourier series. Then we'll try to see how we can take Fourier series and converge to a Fourier transform. So we'll start our discussion with Fourier transform today. We'll build on it after we come back from the break. So this is the last example that we did. Last class, this was the last example. This was using the time multiplication property. If you are going to be multiplying two time domain signals that are periodic, then their Fourier series coefficients get convolved, discrete convolution, right? So the first thing that we did was found the Fourier series coefficients of a periodic square wave, found the Fourier series coefficients of a cosine, and then when you multiply them in the time domain, you are going to be convolving AK and BK. And because this resulted in convolving things with a impulse, unit impulse, it was very, very convenient for us to express the sinks shifted to k minus 1 and k plus 1, right? So that's what we did last time. Now, try to imagine the resulting waveform. When you multiply this guy with this guy, what are you left with? Things between pi over 2 and pi cancel out, right? So you remove this and you remove this. So you get something like this, right? And so on. You get half cycle, 0, half cycle, 0, half cycle, 0. Now, try to think about variations of this. What would you need to do if you had something like this? Let's say after current template. If you wanted to figure out Fourier series coefficients of something like this. This is too big, right? One will do it. Okay. Still too big, I feel. What would you do here? Find the Fourier series coefficients of this. And between, say, negative, what are we saying? Negative pi over 2 to pi over 2. Say negative pi over 2 to pi over 2. It has a cosine t function. And then it repeats. What are you going to do with this? Differentiate twice, you get back cosine again, right? So with this, if you use the differentiation property, you are not going to be able to go a long way, right? Because you see, you have got the cosine, you differentiate sine, differentiate again cosine, and you're back to where you started. Instead, so if you looked at a cosine, it would be something like this. And we know the Fourier series coefficients of that guy, right? There are only two of them, at 1 and negative 1, 1 over 2 and 1 over 2, right? Half and half at 1 and minus 1. Go ahead.
We offset the square wave.
Why offset? Why not just do this? Create another one, right? So you have one square wave that is capturing these guys, and then you have another square wave but flipped, minus 1, capturing these guys, flipping it, right? So you would need, so what you can do is something like this. You can say, I've got that's your one square wave, and it's in a standard form, you know the Fourier series coefficient of that, plus this. Also in the standard form, no, it's not in the standard form. What do you have to do with this? Flip it, right? Flip it and shift it. So you have to do the scaling, amplitude scaling property, time shifting property you have to be used. And then you can find out some BK for this and some AK for this, right? Once you find those out, the Fourier series coefficients of both of them combined will simply be the addition, AK plus BK. Now you will multiply this with the Fourier series coefficients of the cosine signal. You guys see that? And you're multiplying in the time domain. So you are convolving in the Fourier series. So you compute that, add to that, convolve with the impulses, the two impulses that you will have from the cosine. You guys see that? Next question. The Fourier series coefficients of this guy, will they be complex or will they be purely real? Good. Purely real, right? It's a real and even function that you have over here. So the Fourier series coefficients are also going to be real and even. Yeah? We have proved this before. Fourier series coefficients of a real and even signal are also real and even. What that means is this: when you get done with all your business of AK plus BK, convolve it with the Fourier series coefficients of cosine, at the end, you should not see any J's in there, right? Now, if you're running into this situation in exam, then try to solve as much as you can, but please write a note. It will simplify further so that you get rid of the J's. Right? If that is the situation that applies to your problem that you're working on, convey to the grader that you are aware this J cancels out, right? Where do you see this? On problem number 3 that is due tonight, you should see this. It's a real and even signal. So your Fourier series coefficients at the beginning will have a lot of J's. But if you stick with it, you will get a real signal at the end. Questions here? Yeah? Next. How about sine? We talked about the Fourier series coefficients of a cosine, right? If I give you guys a quick reminder here, that's what we had for the Fourier series coefficients of a cosine. You got A over 2 with a phase of theta for k equals 1. And the only other non-zero Fourier series coefficient would be k is -1. You same amplitude A over 2, phase of negative theta. And we sketched both of them for absolute magnitude of them and then the phase of them. For the magnitude, we got A over 2 and A over 2. If we just had a cosine, it would be half and half, right? And then think of it like this. If you have a cosine, half of the energy is going in one, half of the other energy is going in the other. And then the phase is theta and negative theta at +1 as k and -1 as k. Right? We did this. Now, if you look at this and try to find the Fourier series coefficients of a sine, we can do that as well quickly. Let's see. I'm going to go back and evaluate this. For a sine omega naught t, what can I write using Euler's? I can say this is e to the j omega naught t minus e to the minus j omega naught t divided by 2j. Yeah? Which means when I compare this with x of t equals a summation of k equals -infinity to infinity ak e to the j k omega naught t, right? That's representing any periodic signal as a projection of the signal onto the set of complex exponentials, which are an orthogonal set. So what would be AK? Well, if you compare the coefficients, the only two things that you will get is A1 and A minus 1. So what do you get for A1? When K is 1, what do you get? This is 1 over here, which means you're talking about this guy, right? So you get 1 over 2j. Yeah? And then A minus 1, -1 over 2j. Yes? Perfect? Okay, so let's talk about the magnitude and phase. What would be the magnitude of A sub 1? The whole class erupts and says 1 over 2 for both. Yeah? How about the phase? Phase of A1 and phase of A minus 1. Uh, 1 over 2j, right? J, so it would be, so multiply and divide by j, you get negative j over 2, right? Negative 90? So you got negative 90 for this guy, negative pi over 2. How about the other guy? Positive pi over 2? What can you say about symmetry in the magnitude of the Fourier series coefficients? Can I say that the magnitude of the Fourier series coefficients are even? Yeah. How about the phase? Odd. That is for a odd signal. Questions here? Write down the sign using Euler's as a using exponential functions, compare coefficients, find out the two non-zero coefficients for the AKs. Yeah? And you can also write it this way. Another way of writing the Fourier series coefficients for a sine. A step k equals 1 over 2j delta of k minus 1 minus 1 over 2j delta of k plus 1. You guys agree with that? You can also write it this way, right? At 1 and at negative 1. At 1 it is 1 over 2j, at negative 1 it is negative 1 over 2j. This is essentially writing this using unit impulses. Questions about this? Once, twice, wait, okay, hold up. Why do you only have the A1 and minus 1 values? Okay, so here, if I wanted A2, that would have A2, right? So if this was 2, forget about this. If this was 2 here, that would need to be 2 there. But there's no 2 there or no 2 there, which means that all the other Fourier series coefficients are essentially 0. All right, I hope that answers your question, Alan. Let us move forward to Parseval's theorem. Parseval's theorem, another iconic theorem, which essentially says this. If you find the power of a signal, does it matter where you are observing the signal? You have the signal in time domain. You have the same signal in frequency domain. Does it matter? Does it change the power of the signal? Does it change the way you represent it? No, the power in the time domain should equal the power in the frequency domain, right? Because it's the same power, the same signal. That's what Parseval's theorem proves. If you evaluate the power in one domain and if you evaluate the power in the other domain, they should be the same. So we'll try to say the statement, or sorry, we will try to summarize this at the end of this theorem that we will prove. We'll go through the proof rather quickly here. Suppose x of t is your continuous time periodic signal. What is the time period? Cap t. Next, if that is the case, then I can represent x of t as this sort of summation. What is this summation? Projections on a set of complex exponentials that belong to an orthogonal set of functions. That. Now let's also consider the complex conjugate of x. What is that? Well, we know that if the signal gets complex conjugated, then the Fourier series coefficients for that will have a conjugate symmetry, which means ak will equal a sub minus k conjugated. This was called what? Conjugate symmetry. We looked at it in the last lecture. When you have x of t going to x conjugate of t, then ak will become a sub minus k conjugated. So there is a complex conjugate and also flipped about the y-axis. But the same function, e to the j k omega naught t. So that's called what? Conjugate property. Last lecture we discussed this. Next, let's try to multiply these two guys, x with x conjugate. Why are we doing that? Think about it like this. When you want to evaluate magnitude z squared, what do? Z is a complex number. When you multiply z and z conjugate, what do you get? Magnitude of z squared, right? Properties of complex numbers, you know that. Everybody knows this, right? No? Take a complex number, multiply it with a conjugate, you get magnitude squared of the number. Yeah? Why would I ever need this? Well, this is energy in the complex number. So if I divided it by time period, I would get the power, right? That's the reason why I'm trying to go to power. So I'm starting there. That's why I'm multiplying these two. So when I multiply those two, what do I get? I get some other periodic signal with some new coefficients b sub k, right? I need to evaluate them. Some new coefficients b sub k. The summation is going from negative infinity to infinity, e to the jk omega naught t, right? Where bk is what? Ak discrete convolution with a sub minus k conjugated. Where is this coming from? It is coming from the multiplication property. In time, you have multiplied the two signals, x and x conjugate. So in Fourier series, you will have to do a discrete convolution. You have done the discrete convolution of these two guys, and you have called it bk. Bk becomes there. Now, I want to ask you guys this. If I take a periodic signal, and if I take another periodic signal of the same time period, when I multiply them, will I have another signal that is periodic? Absolutely. What will be the time period? Exactly the same, right? So if I have a time period t signal, another signal that has the same time period t, I multiply those two guys, I will get another signal that is periodic with the same time period, which is why we are able to say that this is going to be represented in this form with the same time period, which means the same omega naught. The only thing that changes is the Fourier series coefficients. You see that? And the Fourier series coefficients, you obtain that by doing a discrete convolution there. All right, so let's now try to evaluate b sub k. We have seen the discrete convolution formula many times. What is that? Summation of m going from negative infinity to infinity. What was that? X of m, h of n minus m, right? We are just representing the same thing, but with different n and m values. So b sub k equals, so try to compare it this with this. This was our discrete convolution. Right? We are doing the same thing, but with instead of m, we have L, and instead of k, we have n. So k here gives you k, n here gives you n, m here and m here, L here and L here. You are doing the summation over L, right? So I hope that matches up really well. Next, instead of x of m, what do you have? A sub L. Why? Because this is A sub k. Next signal, A sub minus k conjugated. So this one will be A sub minus the other one, which is what? N minus m. So over here, k minus L conjugate. Let's try to simplify this. L going from negative infinity to infinity, AL remains as is. And over here, A sub minus k minus L can be simplified to A of A sub L minus k. The conjugate remains as is. So far, so good? Yeah? Good. Yes. So this one can be obtained by taking A and taking A sub minus k. Sub minus k means what? Flipped it about k. And then conjugate means what? The amplitude have become conjugate. A plus jb has become A minus jb, right? So their values have changed. Amplitudes have changed. Then you're taking this and doing the discrete convolution, which means fix one, move the other, and then evaluate, right? Flipping and shifting. That evaluation result, which is going to be almost what? Double the number of elements in A, that is what our BK is. So it's the result of the convolution. So the number of elements are going to be almost one less than twice the number of elements in A sub k. All right. Other questions? All right, let's see. The one over here at the top is the last thing that we wrote before. So that's just for reference. Now, observe this. Let's try to evaluate B sub 0. So that means that you are putting a 0 in there. So that means for k equals 0, you are putting a 0 everywhere. What is that going to equal? B sub 0? Well, B sub 0 is the average value of your BK, right? The signal that you get after you multiply x and x conjugate. So that is going to be 1 over t integration over one time period, multiplication of the two signals dt. What is that? That equals, you put a 0 everywhere over here. What do you get? L goes from negative infinity to infinity, AL remains as is. Over here, k goes to 0, so you get A sub L conjugate. AL multiplied by AL conjugate. Note this property. You multiply a number with the complex conjugate of the same complex number, you get magnitude squared. The magnitude of z is magnitude of z, the two vertical lines. So using this, you can say this. On the left, what do you have? 1 over t. Let me try to map this for you. 1 over t here, 1 over t there. Integration over one time period, integration over one time period. X multiplied by x conjugate, what do you have? Magnitude squared. That's your left hand side. On the right hand side, what do you have? Summation, summation. AL multiplied by AL conjugate, magnitude of AL squared. Yeah? A's are complex. So by using this, we were able to derive Parseval's theorem. Next, I'm going to get rid of all of this. Maybe I'll leave it. What is this? That is essentially power in X. But you are evaluating it as a time domain signal. You see, that would have been energy. When you divide it over one time period, you get power in X. This was what? Lecture 1 or lecture 2 of the semester, right? Evaluating power of this signal. On the right, what do you have? You are taking every Fourier series coefficient, you are evaluating the magnitude squared of that Fourier series coefficient, and you're summing up all of those. That is essentially evaluating the sum of powers in all harmonics. So Parseval's theorem proves that the power of a signal evaluated in the time domain is the same as breaking the signal onto all those projections and taking all the powers in each harmonic, adding them up to get your right hand side here. Right? So the power evaluated of a signal, if you evaluate it in time domain or as the sum of powers in all the harmonics, will be the same. And it makes sense, right? I have a point, I have projected it on X and I have projected it on Y. I've essentially broken up X into those two projections. So if I sum up the power of the projections, I should get back the power in X, power in that point. Questions about Parseval's theorem? 1, 2. Trigonometric Fourier series. Why trigonometric Fourier series? Well, one orthogonal set of functions was complex exponentials. But that is not the only orthogonal set that we have. Another orthogonal set can be a cosine and a sine. Those are also orthogonal functions. So let us see if we can represent any continuous time signal that is periodic in this particular form. You have, earlier you just had a sub k, small a sub k as exponential Fourier series coefficients. Now you have three different ones. A sub 0, that's a trigonometric Fourier series coefficient. Can I say that that's a DC value in my signal? DC value of a cosine, 0. DC value of a sine, 0. So that's A sub 0. That is the only term that is capturing the DC value of x of t. Right? So A sub 0 continues to be the DC term. Next, B sub k, coefficients of the cosine projection. C sub k, coefficients of the sine projection. Over here, k is going from 1 to infinity. So x of t is essentially broken down into projections on the cosines, projections on the sine, and a DC term. And when you sum them all back, you should get x. So now let's try to evaluate some properties of these trigonometric Fourier series. Start with this exponential Fourier series. X of t represented as those summations of all those projections onto an orthogonal set of complex exponentials. Next, we are going to assume that x of t is real. If x of t is real, then we have conjugate symmetry in the Fourier series coefficients. Proved this in the last class, right? AK conjugate is A sub minus k. Actually, we didn't prove this. We proved something else. What did we prove? When x of t is real, we proved that AK is equal to A sub minus k conjugate. That's what we proved. But again, if you conjugate both sides again, you get back this, right? Can you see that? So that's conjugate symmetry. If x of t is real, then that is the property its Fourier series coefficients will have to satisfy. Again, this is something that we proved in the last class. So now let's use the conjugate symmetry into this summation. What do you have? X of t equals summation of k equals negative infinity to infinity ak e to the jk omega naught t. So this is exactly the same as this. This exactly the same as this. What you are doing next is breaking this summation into three pieces. One is negative infinity to negative 1, 0, 1 to infinity. Same summation is broken up into three different pieces. After that, let us do a change of variable. Change of variable is m equals negative k. If m equals negative k and you apply it to this guy, you're only doing it for this guy, first guy. K equals negative infinity to negative 1 will change to m goes from infinity to 1. A sub k becomes A sub minus m. E to the plus jk omega naught t becomes e to the minus jm omega naught t, which can be rewritten as k equals 1 to infinity. Why can we do that? If you sum up, it's not integration, it is summing up. So if you sum up this way and if you sum up this way, it should be the same. Instead of m, you're changing it back to k. K equals 1 to infinity. A sub minus m becomes A sub minus k. E to the minus j m omega naught t becomes e to the minus j k omega naught t. So you have done a change of variable once, then you have changed it twice, just so that what can you prove? You can prove that this guy is the same as this guy. Yeah? Negative infinity to negative 1 has changed to 1 to infinity. We have done this manipulation for this. You have got a DC term. We have not messed around with that. We have just taken this, went to this, proved that this equals that. But now if you notice, this is a summation from 1 to infinity. This is also a summation from 1 to infinity. So maybe we can combine these two. Leave out the DC term. A sub 0 remains as is, right? But we can start thinking about combining these two guys because the summation is, for both of them, is going from 1 to infinity. Can you see that? Not a good place, man. Questions about this so far? We are doing all of this so that we can combine these this and this. X of t is represented by this, broken up into three summations. We have taken the first piece here and tried to simplify it so that you get two summations that are both going from 1 to infinity. In one, you have ak, in the other, you have a sub minus k for this guy. In one, you have e to the plus jk omega naught t. In the other, you have e to the minus jk omega naught t. So let's try to see if we can combine them. From before, what do you have? Three summations, right? That was the first step. This, we messed around with that, but we left these two guys alone. We proved that this equals that, right? A0 carries over, this particular summation carries over. Once you have that, you can write the first term as a sub minus k e to the minus jk omega naught t. You can write this as ak conjugate. Why? Because x of t is real, right? X of t is real. You can write this as this. How about this? E to the minus jk omega naught t can be written as e to the jk omega naught t conjugate. The remaining two remain as is. A sub 0 carries over, this summation carries over. Further, ak conjugate multiplied by e to the jk omega naught t conjugate. Conjugate of one number multiplied by conjugate of another number is the same as multiplying the two complex numbers first and taking the conjugate. So ak e to the jk omega naught t conjugate there, a0 there, the other summation over there. Now, we know that z plus z conjugate, the sum of two complex numbers, one conjugate, the other the complex number, is 2 times the real part of z. We know that, right? You can quickly see this: a plus jb, z plus a minus jb, z conjugate, 2a, which is 2 times the real part of z, right? So you have got this guy and you have got this guy, a complex number plus the conjugate of the complex number. So a0 remains as is, but now you have got summation of k equals 1 to infinity 2 times the real part of the complex number. That is your trigonometric Fourier series. X of t being represented as a DC term plus summation over k from 1 to infinity 2 times the real part of ak e to the jk omega naught t. Now, if you wanted to find out the Fourier series coefficient, trigonometric Fourier series coefficients, what would you do? For a given signal, you are trying to find out the trigonometric Fourier series coefficients. What are they? They are this, right? A0, BK, and CK. If your goal is to find out the trigonometric Fourier series coefficients for any x of t, what do you do first? You evaluate its exponential Fourier series coefficients first, right? Put it in there, apply the real part of a complex number operator to that, you will be left with what? Either a cosine or a sine, right? Because when you take this and you, what is this? This is cosine cosine k omega naught t plus j sine k omega naught t. So when you take ak multiplied with this guy and take the real part, you will either be left with cosine or sine or both. The coefficients of those will be your trigonometric Fourier series coefficients, bk and ck, cap bk and ck. You see that? But for this guy, it's going to be the same as a sub 0. You guys see how to evaluate trig Fourier series? Find exponential Fourier series, plug it in this, simplify, compare coefficients of sine and cosine terms. Next, some special cases. So this is sort of making the conversation about trigonometric Fourier series coefficients evaluation a little bit easier. So let's try to see if what happens if ak is real. If the exponential Fourier series coefficients of a signal are real, what happens? Well, x of t is going to equal a sub 0 summation over k equals 1 to infinity 2 times simply ak multiplied by cosine. Why is that? ak is real. If ak is real, what is this? Let me, how do I do this? I'll do it here. So you had 2 times real part of ak cosine, not cosine, e to the j k omega naught t, right? I had plus or minus? I had plus. This equals what? 2 times real part of ak cosine k omega naught t plus j sine k omega naught t. When you multiply it out, what do you get? This part cancels out because of the real operator. You get 2 ak cosine k omega naught t. That's what you have over here. Yeah? Now, when you start comparing coefficients, what do you have? This guy is a sub 0, right? What is b sub k? B sub k is the coefficient of the cosine. Go ahead. 2 ak, right? So if ak Fourier series coefficients are real, then those are your trigonometric Fourier series coefficients. Next, if ak is complex, then you can represent it in a couple of ways. Let's try to see. If ak is complex, then ak can be represented in polar form as magnitude of ak multiplied by e to the j phase or argument of ak. Yeah? Magnitude of ak can be evaluated as the magnitude of any complex number. Square root over real squared plus imaginary squared. Square root over real of ak squared plus imaginary of ak squared. How about the phase or argument? Tan inverse of imaginary over real. You guys have seen this like years ago, right? Evaluation of magnitude and phase of a complex number. Now, if that is magnitude and this is phase, you can plug this over here and over here to get ak. So what would be ak or x of t? How can you write x of t when ak is complex and represented in polar form? Well, you can write it as a sub 0 that carries over, no problem. What are you left with? You are left with summation a equals 1 to infinity 2 times real part of ak multiplied by e to the jk omega naught t. Now, 2 times real part over here, because I don't need to do that for magnitude. The magnitude of a complex number cannot be other than real. It cannot be imaginary. So you can pull it out of the real operator. You're left with what? E. So this part is left over, and you're also left with the phase term because of this. The only thing that you were able to pull out of that real operator is this guy. You pulled it out because that has to be real. Now, can you simplify this a little bit? Well, e to the jk omega naught t, we know you can write it as a sine and a cosine, right? Cosine plus j sine. How about this? E to the j argument. Well, again, cosine and sine. You have a cosine plus j sine here. You have a cosine plus j sine here. 2 terms there, 2 terms there. You can do a FOIL. You can simplify. And then when you apply a real operator, what do you have? You will be left with cosine of the 2 angles. Remember this simple property. This will help you in later on in the course as well. If you have multiplication of 2 cosine, cosine A multiplied by cosine B, you will get 2 other terms. You will get cosine of the sum of the angles, and you will also get cosine of the difference of the 2 angles. Right? So cosine of the difference of the 2 angles is imaginary, which is sort of getting cancelled out, but the cosine of the sum of the 2 angles is staying there. You can also reach the same conclusion by applying the trigonometric properties, and you will also see that. You see what we are doing here? We are representing this as cosine plus j sine, and this as cosine plus j sine. Multiplying these two guys, you will get 4 terms. There will be only 2 terms that are real. When you simplify them, you will be left with this: cosine k omega naught t plus argument of ak. So if ak is complex and represented in polar form, by representing it in polar form, you can evaluate the trigonometric Fourier series coefficients this way. Next. If AK is complex and you're representing AK in Cartesian form, real plus J times imaginary, then A sub 0 remains as is, K equals negative infinity to infinity, 2 times the real part of AK cosine K omega naught T minus imaginary part of AK sine K omega naught T. Again, it's being derived from the same form. The only thing that you have to sort of take care of or remember or refer to is this for Fourier series, for trigonometric Fourier series, right? That's it. You need this, and of course you need that, because you are going to have to compare coefficients. Next. Now, if you represent it in this way, it becomes easier to directly compute cap A sub 0, B sub k, C sub k, right? Because what B sub k is going to be this, right? And C sub k is going to be that multiplied by 2. You see that? B sub k is the Fourier, trigonometric Fourier series coefficients for the cosine terms. These are your cosine terms. So it would be 2 times real part of AK, that's your BK. And your CK is the sine terms. 2 negative imaginary part of AK. Question so far? Quick summary. No summary? Take a signal, project it onto a bunch of orthogonal functions. We considered them to be a complex set of complex exponentials. It was convenient because it was easier to find A sub k. Why was it easier to find A sub k? Because when you multiplied this A2 to find out A2, there was only one term that was giving you a non-zero result. Everything else was canceling out. Magnitude of any orthogonal function over there is 1. The only thing is it's changing with a phase with an integer multiple k. That's the only thing that was changing there. So given a periodic signal, we were able to compute exponential Fourier series coefficients. Actually, we were able to go back as well. Given the exponential Fourier series coefficients, you can make up the x of t. One was a summation, the other one was the integration formula. And then we looked at the properties. Some of the good ones were what? Derivative property was good. Time shifting property was fairly good. I think derivative property, you guys are going to like that. Multiplication property is also something that I really like, because you can sort of be a little bit more creative with the multiplication property. And another excuse to do some discrete convolution. See, if as long as things can be easily put in impulse form, I think that's okay, right? Impulse or even array algorithm, discrete convolution. It's not like we are doing the case by case graphical convolution. All right. Next, we went on to trigonometric Fourier series. Why stop with the exponential Fourier series coefficients that are belonging to a set of complex exponentials? Let's expand that to sine and cosine, because even those are orthogonal. So when you do that, you get some properties, apply some special cases, be able to compare things so that you can find A, B, K, C, K. Next, response of LTI systems to cosine inputs. There is another interesting aspect of LTI systems where you can find the output of LTI systems specifically for cosine inputs very conveniently. Let's try to take a look. You have cosine omega naught t as an input to this LTI system. What would be the output? Let me call this x of t, and this is h of t. What is y of t? What do you guys say? How do you find this out? Don't look at things below this. Just look at the first question. You are given input, you are given h of t. How do you find the output? What? Which one? There are two types, right? Continuous, there is discrete. continuous. All right, so continuous convolution would be the answer. I would take x of t and I would do a continuous convolution with h of t. Yeah. So here is what I'm looking at right now. Cosine signal that is being convoluted with h of t, right? So it's something similar to one of your exam problems where you had a rectangle and you had a sine or a cosine term that you had to do a convolution with. Not straightforward, right? Go ahead, Franklin. Right. So cosine is periodic. However, you would have to evaluate that across any h of t. I don't know h of t, right? So it could be, periodic again, or it could be aperiodic. It could be triangle, square. Depends on the system. But I would have to do this convolution operation, which, let's put it this way, may not be straightforward. Yeah, it may not be straightforward to do it this way. Do a continuous time convolution. Instead, because cosine has how many frequencies? Only one. I can use some other techniques to evaluate its output. Let's talk about that. The input of a system is e to the st. What is the output? The system is LTI. What are the eigenfunctions of an LTI system? You guys have seen Laplace like since childhood. So long time ago. What are the eigenfunctions of an LTI system? The answer is on the slide. E to the st, right? So output should be e to the st. Those are your eigenfunctions of LTI systems. The only thing that changes is what? You multiply it with h of s, right? You multiply it with the eigenvalue. What is the eigenvalue? H of s, which is what we call what? Laplace transform of h of t. Right? This is what you call Laplace transform of h of t. That's the eigenfunction. Sorry, this is the eigenvalue. That is the eigenfunction. E to the st is the eigenfunction. So if your input is e to the st, you didn't have to do convolution. You were able to right away write the output. Can I see that? Next. E to the plus j omega naught t. What is the output? We derived the general case, so this should be even easier. We did e to the st, so everything s is what? S is S is sigma plus j omega, right? So it has both the real part. It's a complex entity. It's not just purely imaginary. So in the next one, we have a S as simply imaginary, j omega. There's no real part. So what would be the output? H of j omega 0, right? Multiplied by? Excellent. What are we doing here? We are evaluating the Laplace transform of the function. We are plugging in s as j omega naught. We got h of j omega naught multiplied with e to the j omega naught. That's the function itself. That's your output. Next, let's do it for the next one. What do you have? E to the minus j omega naught t. Let's zoom out. What is y of t here? H minus e minus. Oh, is that okay? Yeah. What is the cosine? Cosine t is e to the j omega naught t plus e to the minus j omega naught t divided by 2 thanks to Euler's. So use linearity property of LTI systems and tell me what the output is going to be. You simply take this, add this, and divide by 2, right? So I'm taking this guy over here, and I'm taking this guy over here, and I'm dividing it by 2 to take care of this half. Just applying the linearity property. Of course, it's an LTI system, so I should be okay. You guys okay with this so far? It gets easier. So y of t at the top over here is simply whatever I wrote at the end over there, right? So this is, I'm rewriting this over here. I can simplify it a little bit. If the system impulse response is real, then I can say H conjugate of j omega is the same as H of minus j omega naught. Where have you seen something like this before? If a signal is real, conjugate property says AK equals A sub minus K conjugate, right? The same property when you apply it to continuous frequency instead of discrete case, if you apply it to continuous frequencies, you get this. H conjugate of j omega naught is the same as H of minus j omega naught. Now, if H of t is real, only then you can say that. Now, let's use this in this guy. Y of t is half because of this. So there too, that half taken care of. Next, e to the j omega naught t multiplied by h of j k omega naught, that's right here. Plus, what do you have next? E minus j omega naught t h of minus j omega naught. I know that this equals what? This conjugate, right? So I'm writing that over here. Conjugate operator is pulled outside. This guy, I'm taking it over here, but again, conjugate operator is outside, right? You see that? So all of this, using this is here. If you consider this as a complex number C, then this will be the conjugate of that complex number, C conjugate. So what do you have? Half of C plus C conjugate. C plus C conjugate is 2 times the real part of C, right? Or if you write it in polar form, consider C to be in polar form, R e to the j theta, where R is the magnitude of C, theta is the phase of C. C is a complex number. If you want to do C plus C conjugate, then you are really doing R e to the j theta plus R e to the minus j theta, which simplifies to what? 2R cosine theta. Pull out the R, what do you have? E to the j theta plus e to the minus j theta. Using Euler's, you can write that as 2 cosine theta. So it would be 2R cosine theta. What would that be for? C plus C conjugate. So what are you doing? You're taking this guy and you're substituting it over here in the square brackets. Half over here cancels out with the 2 over there. You will be left with what? R cosine theta. What is R? R would be the magnitude of C. What is the magnitude of C? H of j omega naught, right? So you got the magnitude of C over there, magnitude of H of j omega naught. Next, cosine theta. What is theta? Well, theta is the phase of C. What is the phase of T? C. J omega naught. Sorry, omega naught T. Omega naught T goes over here. But also there will be some phase contribution from H of j omega naught. So the phase of H of j omega naught gets added on to that. The output of the signal is magnitude of H of j omega naught multiplied by cosine omega naught T phase of H of j omega naught. Questions about this proof? The proof may not be that interesting, but the application of this proof, I bet, will be interesting. When we start applying this to find out the output of systems, I hope you guys will like the fact that you can, you don't need to do the convolution for these kind of things. For cosines, you can directly write the output. Questions here? Next, let's try to do this. I have an LTI system its impulse response is h of t. And the input to that is a cosine omega naught t plus phi. I want you guys to tell me the output of this system without doing any convolution, any involved math, like any math at all. Let's try to directly write the answer. The only thing that we have is this. So I'm going to have to do this, right? How about the A? If I have the A, what will change? Because now, so this was for cosine. That was for cosine omega naught t. If you have A cosine omega naught t, what will change? You will have A at the front. You will multiply it with the magnitude of j omega naught. Why is this guy being... A magnitude h j omega naught. Who tells me omega naught? The input signal tells me omega naught, right? So cosine 2t, this would have become what? H of j2, right? So the input frequency is what is determining that. Next, what do you have? Cosine omega naught t. Okay, that's just from the input signal, input cosine. Plus, what do you have? Phase of h of j omega naught. What else are we missing? Plus what? T. Isn't that fun? The only thing that we had to evaluate is Laplace transform of h of t. The moment you have Laplace transform of h of t, that's it. You have this, you have this. Everything else is directly in the input, the input signal itself, right? If you have, say, 2 cosine 5t plus pi over 2, this becomes 2, this becomes pi over 2, this becomes 5t. And if you will evaluate this as 5, you will evaluate that as 5. That's it. Now, there are other ways of thinking about this. If a cosine comes in to an LTI system, the output will change in two ways. One, amplitude, the other, phase, right? That's the only way it's changing. Amplitude is changing and the phase is changing. How is the amplitude changing because of the system? Right there. You evaluate the magnitude of the transfer function at that frequency, and that's how it's getting modified, the amplitude of the output. How about the phase? You evaluate the phase of the frequency response really at that same frequency, omega naught. And that's how your phase is getting modified. Everything else is remaining as is. You see, the A, input signal, cosine omega naught t, input signal, phi, input signal. Everything else is the same. The only two things are amplitude is getting adjusted, phase is getting adjusted. So I hope that you guys find it interesting and a little bit more convenient to find response of cosine inputs for LTI systems now. Questions 1, 2, 3? No? All right, let's get into the next lecture, which is Fourier transform. So what's the difference between Fourier series and Fourier transform? It is the most popular question for today. So, okay, that's good. Fourier series are discrete, AK. But Fourier transform, the result of the Fourier transform operation is continuous, right? So in frequency, one is discrete and the other is continuous, right? Now think about it like this, or there's a lot of ways of thinking about it, but let's go back to that same set of time and frequency relationships, right? What happens in time corresponds to what happens in frequency. So let's start with derivative. If you differentiate in time, what do you do in frequency? You multiplied the Fourier series coefficients by what? J k omega naught, right? You had some j k omega naught getting multiplied, time and frequency, that was it. When you differentiated in time, that's what happened. I also said multiplication and convolution are Fourier transform pairs. If you multiply two signals in time domain, you are convolving their Fourier transforms in the frequency domain, and vice versa. If you're doing convolution in time, you're multiplying things in frequency domain. There's also one more thing that I said. I may have not emphasized on it. If you take one thing and you make it periodic in one domain, what are you doing in the other domain? You are essentially sampling it in the other domain, right? So if you take a signal and you make it periodic in time, you essentially you sample things in the frequency domain. So when you had a periodic signal giving you Fourier series coefficients, they were discrete, right? They were sampled. So when you had a periodic signal, you had sampled things. What is going to happen when you go to Fourier transform? Fourier transform is for general signal. They could be periodic, they could be aperiodic, any signal. You are essentially taking away that periodic nature, right? So if you take away that periodic nature, now things are not going to be sampled, you are going to get a continuous function, but the same envelope. So remember, for a periodic square wave, we had a sinc envelope, but it was sampled. Now you're actually going to see that sinc for just one rectangle, not a periodic rectangle, right? So that's what sort of the difference is between Fourier series and Fourier transform. I will try to demonstrate this in a slightly different form as well. Let's do it mathematically. Where am I doing it? I'm doing it over here. All right. So Fourier series to Fourier transform. The first thing that I would like to do is to show you guys a MATLAB simulation about how Fourier series transforms to Fourier transform. Like, how do we go from Fourier series to Fourier transform? So for that, I have a video that I recorded some time ago that I'm going to share. So for that, I'm going to need this, and I'm going to need this, and I'm going to need Chrome. Where is Chrome? Right here. Okay. Yes. So people online are able to see it, hopefully, and people in the room are also able to see it. All right. People online, are you guys able to see this YouTube page? Okay, sure, good. Excellent. So we are going to try to look at this MATLAB simulation first. When I run this, I'll try to use pause. Okay. So the first thing that I'm doing is, this is case one. Case one is, I have a periodic square wave. On the left, I have the time period of that signal set to 4. And on the right, I have its Fourier series coefficients, AK, right? If time period is 4, I know that omega naught is going to be pi over 2, right? 2 pi by 4, pi over 2. On the y-axis over here, I am evaluating that as t times AK. So the coefficient, Fourier series coefficients AK multiplied by the time period t. And on the x-axis, instead of looking at 1k, 2k, 3k, I'm actually looking at k omega naught, 1 omega naught, 2 omega naught, 3 omega naught, and so on. So depending on t equals 4 and omega naught equals pi over 2, you see when t is 4, omega naught is pi over 2. So that's going to be the difference between each sample, right? Pi over 2, pi over 2, pi over 2, pi over 2, and so on. Now, imagine that this time period is increasing from 4, 8, 16, 32, 128, all the way to infinity. What is going to happen to your rectangle? And consequently, what is going to happen to your Fourier series coefficients? Let's try to take a look. If I go one step ahead, I'm going to case number 2 here. Time period is 8, omega is pi over 4. What happened? The samples became closer to each other, right? Because omega naught here is pi over 4. So you're sampling, you're getting at what? K omega naught, plus and minus pi over 4, plus and minus pi over 2, plus and minus 3 pi over 4, and so on, right? So as these pulses are getting spread apart in time, this is getting more and more continuous. Can you see that? Let's take a look. Let's keep going. And you can extend this out to infinity. So go to time period 16. Omega naught is pi over 8. Closer. Same shape, just samples are getting closer. And then this is 32, and then it is 64. You see the sync getting more and more continuous. And then 128, this is where it will stop. Omega naught is pi over 64, right? So bottom line is, if you had a periodic signal where you essentially extended that time period out to infinity, instead of having a sampled sync, you would get a sync function, a continuous sync function. That's how you go from Fourier series. That's how Fourier series converges to a Fourier transform. You see that? So we're essentially going from periodic signals to any signal. Generally, you will not have a periodic signal. You will most likely have a aperiodic signal. One pulse, one square, one triangle. That's it. Good. You can do that, yes. So you can have a Fourier transform of the entire periodic signal, yes. Because Fourier transform is for all, periodic and aperiodic, but generally it's for aperiodic. Okay, now let's go back to the slides. How do we go back to the slides? I should start sharing. WebEx, share, screen, start. All right, I think we are back, right? You guys can see it online. You guys can see it over here. Excellent. Okay, so we did this. We saw how Fourier series converges to a Fourier transform. Essentially, pull out the signal, make it just one period, one time period. And what it does in the frequency domain is puts more and more and more and more samples between each of those samples, making it more continuous. So signal classification versus Fourier series or Fourier transform. So if you have a periodic signal, then the transform that you will use to evaluate its frequency content is Fourier series. And the notation for that is x of t, double-sided arrow, Fourier series, ak. Why double-sided arrows? Because for an x of t, you have a sub k. And given a sub k, you can evaluate x of t. Now, for a general signal, which means both aperiodic as well as periodic signals, you evaluate Fourier transform. And the way you write out Fourier transform is, on the left, you have the time domain signal, x of t. And then you write ft on top of it. Or you can also write something like this. Oh, too big. All right. Fourier transform. On the right, what do you have? Cap x of omega. So on the left, in the time domain, you use small letters, x, m, s, whatever you have, but small letters for time domain. But for your frequency domain, you use cap x. You just now saw, for Laplace transform, you used a cap h, right? Now, there are other ways of this as well. Cap x of j omega, or that's it, either omega or j omega. These are the two popular forms for that. That's the Fourier transform. In one, the signal is dependent on what variable? Time. In the other, the signal is dependent on omega, frequency. Oh, by the way, I can also do this. Frequency, f, right? So omega or j omega or f. All of these correspond to Fourier transform of signals. Now let's try to derive that for a rectangle. What would be the Fourier series of this guy? Periodic square wave, right? So it would be a sampled sync, right? Which means if I looked at just one pulse, what would be the Fourier transform of that? A continuous sync. The one transform pair I want you guys to get sort of associated in your head is this. Rectangle in one domain is going to be a sync in the other domain. Notice the double arrow. That means if the sync was in time, you would get rectangle in the frequency. rectangle and sinc are Fourier transform pairs. Now here is a bouncer. A triangle signal is going to be what? Use the skills that you have so far and try to tell me what that is going to be. Go ahead. It would be sinc what? Derivative of sinc. No. So here, how do you get triangle? So here, rectangle is a sinc. Right? Think about all the properties you can use. Because they're almost there. So how do you get a triangle? What do I need to do to rectangles to get a triangle? No. Triangle. If I integrate, I'll just get a ramp. I need a triangle. I have rectangle. Convolve it, right? So if I convolve two rectangles, what do I get? I get a triangle. So what am I doing? I'm doing a convolution in time domain. Sinc squared. You see that? All right, next, trapezoid. So I have a trapezoid in one domain. I don't know which domain, maybe time, maybe frequency. What is it looking like in the other domain? The two sinc functions, exactly. Right? Because it's not sinc squared anymore. For those, it was sinc squared because there was the same rectangle getting convoluted. Was that? Oh, multiplied. Sorry. Sinc multiplied by another sinc. Two sincs. Where have you seen like a triangle? Sorry, not a triangle. Where have you seen a rectangle? Maybe not in a time domain, but in some other domain you might have seen a rectangle. Circuits class, last chapter, what do you do? At the end of circuits, you guys do body plus. Before that, what do you do? You do filter somewhere, right? Okay, so okay. Ideal filters look like what? Ideal filters look like rectangles, right? So what is the impulse response of ideal filters? When you say this, is it in the time or is it in frequency? Frequency is a rectangle. So the impulse response should be what? Time. So based on this, it should be sinc, right? The impulse response of ideal filters, like a low pass filter, is going to be a sinc. You see that? How about a realistic? Trapezoid looks a little bit more realistic, right? Like a filter. Trapezoid filter looks a little bit more realistic because you're allowing a slow roll off. For this, the impulse response would look something like multiplication of two sincs that are different, right? Two different sincs. Yeah? Getting interesting a bit, maybe? No? All right, let's go back to some details here. I'm not kidding. I want you guys to see these things as pairs. Rectangle sinc, triangle sinc squared. Get that association in your head. Yeah. Next, x of t, the Fourier series coefficients are a sub k. For a pulse train, this was what? This was our pulse t1 comma t, right? Time period is t. It is on, or it is 1 from negative t1 to t1. The Fourier series coefficients of this guy we computed earlier as this. ak equals 2t1 divided by t sinc k omega naught t1 for all k. That's what we had derived earlier. Now, if you write it in a different form, we know that sinc x is sine x over x, right? And even in the reference sheets that you might have glanced over a little bit, some of these functions are represented like that, sine x over x, not in the sinc function, but using a sine function. They are exactly the same, just different ways of representing. So sinc k omega naught t1, you can break it up as sine x over x, t1 cancels out, and you will be left with 2 sine k omega naught t1 divided by k omega naught t. Now, let's try to do some manipulation here. Let's bring this t onto the left-hand side. What do you have? AK equals AK times t, which is the time period. Why didn't I leave it over here? I didn't want to leave it over here is because I'm playing with that time period, right? Keep on extending it. I'm making it tend to go to infinity. So I don't want that to be in my denominator. I want it to be on my numerator on the left-hand side. So AK multiplied by T equals 2 sine k omega naught T1 divided by k omega naught. Next. Now AK multiplied by T, that's what I have on the left-hand side, is essentially like sampling 2 sine omega T1 divided by T at intervals of length omega naught. Let's review this statement again. This particular signal here, AK multiplied by T, is 2 sine k omega naught T1 divided by k omega naught. It is like saying I'm essentially sampling 2 sine something T divided by that same something at integer multiples of omega naught, 1 omega naught, 2 omega naught, or minus 1 omega naught, 2 omega naught, and so on, right? So I'm essentially sampling this 2 sine omega T1 divided by omega at integer intervals of length omega naught. See, instead of omega, you put in k omega naught. Instead of omega, you put integer multiples of omega naught, you get back what you had earlier, right? So this would be the continuous function that was getting sampled at k omega naught. Yes? So that's your continuous function. The y-axis is over here, t a k. On the x-axis, you have k omega naught. The separation between these two guys, integer intervals of omega naught. The shape, what is it? 2 sine omega T1 divided by omega. When you have omega naught, this separation is this way, right? Now, if you extend that time period, to infinity, omega naught tends to 0. 2 pi divided by t, t goes to infinity, omega naught tends to 0. So what happens to this? The separation between these two guys will become closer and closer, right? So it's, as you are extending that time period to infinity, it is like saying, I am evaluating that same function. It is the same function, close to each other, right? The sampling time has gone down. You see that? So from this, you will be able to go to this. As you push this square wave out, you get more and more samples in the middle. That's what we showed with that demonstration. And if you extend this conversation as t goes to infinity, in other words, omega naught goes to 0, all the frequencies will be represented. It's not just going to be k omega naught. It's going to be all the frequencies, omega. The envelope is going to be 2 sine omega T1 divided by omega. So what do you have? If a rectangle is going from negative T1 to T1, the Fourier transform of that is going to be 2 sine omega T1 divided by omega, which can also be written in sinc form. Multiply and divide by T1, combine sine x over x, and you get 2T1 sinc omega T1. Yeah, we'll prove that. Now let's take a look at the Fourier series integral. We need the Fourier series, Fourier transform integral. We want to get there. How do you evaluate x of omega? How do you evaluate the Fourier transform of a signal? For that, we are going to have to again start with Fourier series, because that's where things are starting. We are just evaluating that from t tends to infinity, right? So let's take a look at the Fourier series in general. You have AK 1 over t integration over one time period x of t e to the minus jk omega naught t dt. We have seen this before. AK multiplied by t is simply integration over one time period x of t e to the minus jk omega naught t. We have just brought this over here onto the left side. Now, as t tends to infinity, we know that AK times t can be considered as sampling of integration over one time period e to the jk. Instead of k omega naught, what did we have? Just omega. A function being sampled at k omega naught. So what would be the Fourier transform? The Fourier transform of x of t, just one rectangle, would be integration from negative infinity to infinity x of t e to the minus j omega t dt. And maybe you can relate the Laplace transform to this as well. X of s is integration negative infinity to infinity x of t e to the minus st dt, right? It looks very similar, except s is purely imaginary here, right? So why have Laplace transform at all? We have Fourier transform, right? Why do we need Laplace transform then? Okay, there is time, there is frequency, I have time, and I have now frequency, then why do I need s? Why am I not done with omega? Okay, here is an integral. Will it converge? An integration operation, will it always converge? Maybe, maybe not, I don't know, right? There are certain conditions with when the Fourier transform of a signal can be computed, converges to a value. But if those conditions are not met, you may not get that integration to converge to a particular value. What do you do then? You stop evaluating the frequency content? No. You evaluate the Laplace transform of the time domain signal and then define a region of convergence. Here is my region of convergence where this integral will converge. Here it will not converge. Right? So that's the reason why we look at Laplace transform and not just the Fourier transform for everything, right? Because that integral may not converge. Going okay? So that's what we are going to call the Fourier transform of a signal. You want the Fourier frequency content, you integrate from negative infinity to infinity, put the time domain signal in there, multiply by e to the minus j omega t dt. The difference is what? Omega, continuous frequency variable. Earlier, omega naught was constant, depending on time period. K was an integer, right? That was the difference. Now, let's go the other way. How do you find out inverse Fourier transform? Why would I be ever interested in inverse Fourier transform? Well, sometimes you want to go from t to f. Sometimes you want to come back from f to t. In that case, you need inverse Fourier transform. For inverse Fourier transform, I'm going to try to walk through this very quickly because I want to get to a little bit of a sort of a mature discussion about Fourier transform, or a little bit more interesting discussion about Fourier transform. Why do we need it? What all information can it give us? X of t is a summation over all k e to the plus jk omega naught t. Sum of all the projections. AK multiplied by t is the Fourier transform of a signal, but when omega is evaluated at k omega naught. So you can say that as x multiply x of jk omega naught. Instead of saying x of j omega, you're saying instead of omega, you're saying k omega naught. So what would be AK? AK would be 1 over t, the Fourier transform of the signal evaluated at jk omega naught. Not evaluated at jk, evaluated at k omega naught. Instead of omega, you have k omega naught. I hope you see that the j should not be throwing you guys off, right? Sometimes you say x of omega, sometimes you say x of j omega, sometimes you say x of f. Just different ways of expressing the same function. X of t is the summation over all k of ak from here multiplied by e to the plus j omega naught t. Right? You have just put in ak into this for x of t. One over t can be written as omega naught divided by 2 pi. So omega naught goes over here, 2 pi comes over here. K from negative infinity to infinity remains as is. Fourier transform evaluated at k omega naught remains as is. E to the j k omega naught remains as is. Now, as omega naught tends to infinity, why omega naught tends to infinity? Because when you're taking the Fourier transform, Fourier series, how do you go to Fourier transform? You go t tends to infinity. As t tends to infinity, omega naught tending to 0. So as omega naught is tending to 0, this particular function is the Riemann sum, right? Height, the approximation of a summation. This is the width of the rectangle. This is the height. This is the width of the rectangle. This will be the height of the rectangle, right? Width, height, width, height, width, height. You know it's going to be a numerical approximation of an integration. You get 1 over 2 pi over here. Integration becomes from negative infinity to infinity. this guy becomes x of j omega, a continuous function. This guy becomes a continuous function as well. He's a plus j omega t d omega. So if you want to go from frequency to time, put the frequency domain information there, multiply by e to the j omega t, integrate out omega, you will be left with t. You'll also have to take care of this 2 pi, 1 over 2 pi. So that would be a formula to compute inverse Fourier transform. On this slide, you have formula to compute Fourier transform. Should I always use this formula to compute Fourier transform, an inverse Fourier transform? The answer is only at the beginning you will use these things. But as soon as you get some standard forms and then properties, you will hardly need to use this, right? So your goal should be to use the tricks and the properties and the standard forms. Your goal should be to avoid using this as much as possible. Yeah, at the beginning you need to learn how to use it. However, you should try to stay away from this as much as possible later on. Let's see, we need to have this discussion about definition of Fourier transform. Let's try to see. You have x of omega or x of j omega or x of f, all of those defined as integration from negative infinity to infinity time e to the minus j omega t dt. One thing that commonly gets mistaken here, there is a minus over there, there is a plus over there. So when you want to go from time to frequency, there is a plus. Sorry, from time to frequency, there is a minus. From frequency to time, there is a plus there for the exponential. And also the 1 over 2 pi factor. 1 over 2 pi factor is not there, but it is over there. Where is that 1 over 2 pi factor coming from? Omega equals 2 pi f, right? Because I was expressing things as a function of omega, no 2 pi over there. But when I go to time, I'm talking about something that is the reciprocal of frequency. You get that extra 2 pi factor in that case. How are you writing Fourier transform and inverse Fourier transform? This way, x of omega or x of j omega or x of f, capital letter X, is Fourier transform of the time domain signal x of t. How are you writing inverse Fourier transform? F of t equals inverse Fourier transform of x of j omega or x of omega or x of f. Capital letters for frequency domain information, small letters for time domain representation. So what do you have here? On the left, you have a time domain signal x of t, right? And as you take the Fourier transform, you get x of omega. If you take the inverse Fourier transform, you get back your time domain. Other representations, x of j omega or x of f. Do all transforms require integration? Well, we talked about that. All the transform pairs can be found by direct integration. If you do that integration, you will be able to get the answer. However, your goal should be to avoid the messy math. The way you do that is by using standard results, which is essentially your tables, and properties. You will have differentiation property of Fourier transform, integration property, time multiplication property, convolution property, linearity property. You will have all those properties again for Fourier transform. And it's going to be looking a little bit more repetitive. So we'll not deal with all the properties the entire way now that we have proved many of them. But we will still prove some of them. But the idea is to be using them properly to get your answers quick. Avoid the messy math. So sometimes this integration is messy, cannot be avoided. But all the times that you can avoid the messy math, do it. How do you do it? By using those transforms and properties. Now we saw how there are many problems where integration is unnecessary, like I said. If you're seeing this on an exam, you are most likely going to need properties in standard forms and not do the direct integration, right? So everybody thinks I have one way to solve it, let's jump and solve it. But if you do that, the chances are that you will end up doing math for a long time, which may not turn out to be unnecessary. If you do it really correctly, you see how easily we have written this. We have done 3 Fourier transform things over here, rectangle, sinc, triangles. It was so easy, right? Of course, we didn't put in all the numbers in there, but you will get ready to even put in the numbers. But the idea is we avoided the math here, and you should too on the exams. Let's go back to this. All right, so these are standard forms. Operations whose transforms are known. Rectangle sink, known. And then the properties. Will the integral always converge? No, it will not always converge. However, it is guaranteed to converge with two sufficient conditions. There is a weak condition and there is a strong condition. The weak condition is the signal should be square integrable, meaning if you take x of t and evaluate the magnitude squared of x of t and you integrate it, what is this? This is the energy of the signal. If energy of the signal is finite, then the Fourier transform of the signal will converge. That is a sufficient condition, but it's a weak sufficient condition. A strong sufficient condition for the integration to converge is this: the signal should be absolutely integrable. Take the signal, take the magnitude of the signal, integrate it. If it converges, you're good. Is sine integrable? It's going to keep on going, right? So the chances are that you're not going to have that converge. So the signal is absolutely integrable, strong condition, weak condition. All right, we talked about that. Let's talk, how much time do we have left? Yeah, 1 minute. All right, so this is sort of my favorite discussion of, man, all right. Okay, so we will have this, I usually associate like 20, 30 minutes to just this one slide. So I want to have this, because this is, why should I care, right? Why should I care about Fourier transform? That's the answer here. So we'll have that discussion. We'll have that discussion when we get back from the break. When is that? July 12th, I think. So I hope you guys take a break. There is only one way to take a break. What is that? Not like just switch everything off and force yourself to take a break. Not taking it. You guys should talk to him. Like what? All right. So please try to relax as much as you can. When we come back, we'll have this discussion. We'll continue our discussion about Fourier transform. What else? There's a homework due tonight, and there's homework due when you come back. Nothing due in the, at least nothing due in the break. So hopefully you guys are. During